So, welcome to week 5 of Newtonian cosmology. Essentially, we've spent the first 4 weeks of this course deriving the equations that govern the evolution of the universe and looking at what the components of the universe are. And at the end of that, we've come up with a benchmark model for the universe as it is now. And so we have some omega in baryons. So about 4% of the universe is baryons. We have omega dark matter, which is about 0.23. And together, these things make up omega M. Sorry, they're all subscripted 0, which is 0.27. We have omega R, the radiation contribution, which is now roughly 10 to the minus 4. It's very small. And then we have this omega lambda term here, which is 0.73. And that gives us overall a flat universe. And a flat universe is nice, it's easy to compute. And we hold this up. This is a remarkable thing that we've been able to put together this benchmark model of the universe. It's fantastic, except that we don't understand this bit. And we don't understand this bit. So it's great, it's very successful, but we don't really know what 96% of it is. So it's worth bearing that in mind, that, this one, the dark matter, just behaves like matter, so we can know how it behaves. This we can substitute in some equation of state for, W equals -1 or something like that. We can vary our equations of state, but we don't actually know why these things behave as they do, and we don't know what they are. And so it's worth spending a little bit of time, looking a little bit more critically at this model, because successful as it is, it's always a little bit unsatisfying when you've introduced things to make it work that you don't really understand. And so the first thing, and perhaps the thing we have the most leads on, is to try and understand what dark matter is. And that's what we're going to look at mostly today. There is some link to dark energy, but we'll mainly talk about dark matter today. And so there's pretty good evidence now that dark matter is real. And we've already talked about the rotation curves of spiral galaxies. So our Milky Way is a spiral galaxy. And we've said, the orbital velocity is given by the square root of g(m)r over r. And we've basically looked at that in more detail in the past. And we've seen that in spiral galaxies, this becomes a constant at larger radii. So in principle, you expect the mass to be concentrated in the centre, therefore you expect to go beyond some mass and the rotation curve will fall off. That is not what you observe, so you have something R and V here. You would expect it to rise in the middle and then fall off roughly as R to the -1/2 once you've gone past the mass. And what you actually observe is something rather different, because what you actually observe is something which rises and then goes flat. And in the Milky Way, for example, the velocity is about 220 kilometers per second. And it carries on well beyond where you would expect that mass to be. And clearly, the mass must be proportional to the radius, such that it cancels out and you end up with a constant velocity. So mass increases beyond the visible light. That is what dark matter does. But that's not the only evidence you can get. And in particular, it's not always satisfactory because spiral galaxies are only a small minority of galaxies. They're galaxies which have very highly ordered rotation, such that you end up with a disk and this material going around. And so although the prettiest galaxies, the ones we have lots of photos of, are Milky Way, Andromeda, other nearby galaxies, many of them are spirals, lots also aren't. And so what about systems that don't have well-ordered rotation? And, star clusters, galaxy clusters, all of things like that don't have well-ordered rotation. But what we then resort to is something called the virial theorem. And you may have come across the virial theorem, you may not. It doesn't matter if you haven't come across it before. It's actually a very important theorem which exists in mechanics. And basically, it says that if you have some system in equilibrium, if you've let it go for long enough that it's become in equilibrium with itself, a system meets the following requirement. Has the following. It has 2t plus v equals 0. And this is the kinetic energy, and this is the potential energy. So if I look at, say, a star cluster, a galaxy cluster, an elliptical galaxy, all sorts of things, this applies. And so just look at that cluster, right? The cluster has some kinetic energy. And that kinetic energy is just the sum of all the individual energies which exist within it. Right, so I add up all Ke for each component. Imagine this is a system of stars, that's every star, it's a galaxy, it's every galaxy. And of course, I can't really do that because a galaxy contains 10 to the 11 stars or something. I don't want to go and get all the kinetic energies of them individually. And so what I'll say rather more simply is I'll say that's a half times m v squared, where this is now the total mass. And this is what's called the velocity dispersion. And what that means is if I go, for example, and I have a system with lots and lots of stars in it, but I measure a bunch of stars, and they've all got different velocities, and I average the velocities out, and I look at the standard deviation, if you like, the sigma of those velocities, that's the velocity dispersion. So if I use a spectrograph, for example, to measure redshifts, e.g. measure redshifts and get velocities, then I can get the dispersion. And I'll just note, if I do that, I get it in one dimension, so I need to multiply it by 3 if I really care about all 3 dimensions, but I get it in 1. And so I can measure a velocity dispersion and therefore get the full kinetic energy of the system from some observable. So the kinetic energy is something I can get, or I can determine. So that's quite important. Then I need to worry about what the potential is doing. So imagine I have some system, with lots of little stars in it. You've seen this sort of thing before. Don't really want to have to draw too many of them. Well, what I can do is I can split this down into little shells of thickness dr, some distance r out the middle, and I can write, if you like, the contribution of the potential in there. So I can say, this is dV, which is equal to minus Gm, less than R, the enclosed potential, over R, times then the mass in the shell. And the mass in the shell is 4 pi r squared rho dr. So if you think about it, this is the internal mass, my big M, if you like, the internal potential, and this is then my mass in the shell. So in a sense, all I'm writing here is, V is GMM over R, but I'm just defining my potential appropriately, actually not for, 2-point masses, but for some uniform distribution of mass. Let's just assume that this is some constant density, i.e. that rho is not a function of R. It actually is in practice, but let's just be simple about it. And of course, M at less than R is just 4/3 pi r cubed rho. It's just density times volume. So I can write that V is equal to minus 16 over 3 pi squared rho squared integral between 0 and R of R to the 4 dr, just multiplying all of that out, which is equal to minus 16 over 15 pi squared rho squared R to the 5, and then substituting back in for M is 4/3 pi r cubed rho, I can get that equal to minus 3g m squared over 5r. So this potential for a spherically symmetric uniform density sphere or distribution. And you can see, if you wanted to, you could make that more complicated, because you could make rho dependent on R. You could do this integral for some more arbitrary distribution or something that was a bit more squashed or anything. The integral becomes more complicated. And then if I use the virial theorem, right, I can use the virial theorem now to get a mass. And the virial theorem, remember, says 2t plus v equals 0. And I've got, therefore, a half m v squared minus 3gm squared over 5r. Sorry, there's a half. I put the half in here. This is 2t, of course. Sorry, mv squared minus gm squared over 5r equals 0. And therefore I can get that m is just 5 v squared r over 3g. And so what I have here is actually a route to obtaining the virial theorem.